In this video, we'll talk about quantum walks. So quantum walks are quantum analogues of classical walks. And classical walks have been useful in various branches of science, engineering, social science, in modeling behavior, economics, in economics such as stock prices, in devising new randomized algorithms, and so on and so forth. So let's start with classical walks. So in classical walks, we have a person who's or a particle that is on a lattice. So we are talking about one-dimensional walks on a lattice. So we have lattice points labeled 0, 1, 2, and so on. And initially, maybe the person is on lattice point 0, and the one step of the classical walk happens in the following way. A fair coin, let's say a fair coin is tossed. One step of a classical random walk. So fair coin is tossed. And so that is the first part. If the coin is head, the person moves to the right. So right step, take one step to the right. Or else if the coin is tails, then take one step to the left. So either head occurs, then it moves to the right, or a tails. So that's one step of the walk. And you repeatedly do it. So in the case of a classical walk, one can visualize the classical walk also in the following way. So we can plot a graph. So let me just draw a graph of a classical walker. So this is another way of visualizing a walk. So on the x-axis is time or number of coin tosses. And so time is discrete over here. And on the y-axis is the position of the random walker. So this is position of the walker. And so for instance, if the first toss is a head, then maybe the walker is in initial position 0, and then he moves to position 1, and then maybe the second toss is a tail, that the walker moves back to position 0, then head again, and then head, right? So this is a head, tail, head, head sequence that happens. And so this is another way to sort of visualize the walk. And you can scale this sort of walk, and this walk eventually can start looking like this by appropriate scaling and adjusting the frequency at which you toss a coin. And this looks like maybe a stock price. So this is one way to make a classical walk useful in finance or economics. Right now, one can plot the probability distribution of the walker at each and every time step. So, for example, at time step 1, so time 0, the walker is at position 0 with 100% probability, or with probability 1. At time step 1, one could plot the probability distribution of the walker, and you can see that it is distributed on the positions -1 and 1, and each of them is with probability half. And then you can do the same at time step 2. Again, you can plot the probability distribution. So in this case, the walker can either be at -2 or 0 or 2. And in this case, the probability of being at 0 will be half, 1/4 will be -2, and 1/4 over here. So this is the probability distribution of the walker after 2 time steps. So the probability of finding the walker at position -2 is 1/4, position 0 is 1/2, and position 2 is 1/2. And let's do that for one more step. So step 3. Okay, now the walker can be at -3, -1, 1, or 3. And here the probability distribution is going to be so this is going to be 1/8, maybe 1/8, 1/4, and 1/. Sorry, this is going to be not like this, but let me just erase this probability. So one over 8, 1/8. So that adds up to 1/4. And (3/8) and 3/8. Right? So that adds up to 1. Right. So this is the probability distribution of the walker in 3 steps. And you can see that it is symmetric. In fact, it's a binomial distribution. And you can look at this classical walk as a sum of independent random variables. So Sn is a sum, the position of the random walker at time, let me just say time t, is a sum of independent random variables xi, where xi is equal to +1 if head occurs and -1 if tail occurs. Right? And you can compute the expectation of ST. So expectation of ST is obviously 0, and variance of ST is, now we can add up all the variances because these are independent random variables. So this is variance of summation I is equal to 1 to t xi, which is equal to summation I is equal to 1 to t variance of xi. And each xi has variance, what is it? 1 times half plus -1 square times half, which is 1. So this is going to be t, right? Each of them has variance 1. So this random walker has variance t, right? So that's about what I want to say about the classical walks. Now let's go to quantum walks. Now we won't use the term random over here because the quantum walks is is basically a unitary evolution. So it's deterministic. Only when you measure the Walker, finally do you get the randomness due to the measurement. So anyway, let's look at the quantum walks. So we'll create an analogous sort of situation. So the quantum walk happens on a tensor product of two Hilbert spaces. So HC tensor HP. So this is called the coin space. And this is called the position space. And again, we'll look at the specific example of a one-dimensional quantum walk. So in the one-dimensional case, there are 2 degrees of freedom. So in this case, HC will be span of, let's say, right and left direction, because there are 2 degrees of freedom. We'll take these two as up and down, get up and get down. And the position space will be the span of, these are basically two orthonormal bases of two-dimensional space. And in the position space, it will be the positions 0, 1, 2, and so on. And then, so this will be an infinite dimensional space of positions. So, okay, and then again, the quantum walk will be analogous to the classical walk in the following sense, that one step of the quantum walk consists of a toss of a coin. Now, the coin is going to be a unitary coin. So in quantum mechanics, we have this unitary evolution. So the coin is a unitary operator on HC. For instance, one coin that you could think of is a Hadamard coin. So any unitary operator is acceptable, but we can make use of this coin, which is called the Hadamard coin. So this is the Hadamard coin. And so the first step is tossing this coin. You have, let's say, initial state. You can have an initial state. So psi initial of the walker can be, for example, up tensor 0, which means that the walker is initially in a state where the coin state is in the up state and the position state is at the 0 position. Right. And so there are 2 steps. So the first step again is tossing a coin. So you apply the Hadamard gate to this thing, and which acts, so the coin acts only on HC. So coin acts only on the coin space HC. And the second step is the shift state, which is also called the conditional shift. So let me write down the shift operator. So shift operator S is equal to summation I is equal to minus infinity to infinity. So this is an operator, tensor I plus 1, I plus summation. So this will be down, down, tensor I minus 1, I. So this is called the conditional shift operator. What it does is that if the coin state is in the up state, then it shifts the position of the walker from I to I plus 1. And if the coin state is in the down state, then it shifts the position of the walker from I to I minus 1. And this is a unitary operator. And the combined unitary, so combined unitary U that gets applied at, so U is bound operator on acts on its C tensor HP and its C tensor identity into the shift operator. So I should write it the other way because it's going from the coin acts. So from right to left, it's C tensor identity followed by the shift operator. So this is the one step of a walker. So the coin gets tossed, right? It acts on only on the coin space. And then the conditional shift operator, which depending on the coin state, it either moves the walker from right to left or left to right. Now let's take a similar example of the quantum walker on a one-dimensional lattice. Okay, so let's example. So we'll again do the 3 time steps of, so example of quantum walker on a one-dimensional lattice. Okay, so as I said that let's start with walker. So psi initial being up tensor 0, right? So this is the coin state and this is the position. Now let's do 3 steps. So let's say step 1. First, the coin gets tossed. So coin acts only on the coin state. So it's a Hadamard coin. So the coin takes the coin state to up plus down over square root of 2. So this is coin acts on the coin space. So this is the first part of the one step unitary. We have done this part. And now the next is the shift operator. So shift, what does it do? It takes, if the coin is in up state, then it moves the walker from 0 to 1 step to the right. So this is going to be 1. Plus, if the coin is in down state, then it takes to -1. And then we have the square root of 2. So I can write this as down tensor -1 over square root of 2 plus up tensor 1 over square root of 2. Okay, at this point, if we choose to measure the walker, then the probability, so we'll measure the coin space, not the coin space, the position space. And if we do that, then these probability amplitudes will be the probability with which we will observe the walker. So the probability of observing the walker will be -1, 1. And again, it will be 1 over, so the probability amplitude is 1 over square root of 2. So this will be 1 over 2. This also will be 1 over, just like the classical walker, right? So if we measure the walker at this stage, if we choose not to measure, then we can apply the unitary again. And let's see what happens if we go ahead with doing one more step of the walker. So this is step 2. So in step 2, the final state of step 1, which is this state, will be the initial state. And so let's do this. So the Hadamard coin will operate on this. So this down will go to up minus down over square root of 2. So this down first tensor. So I'm just doing the coin first. And there is also 1 over square root of 2 over here. So this is 1 over square root of 2. And then there will be up plus down over square root of 2, 1 over square root of 2, tensor 1. So basically, you get something like this. Something like this. So basically, you get 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 something like this. tensor -1 and then plus. Right now, this is the coin, and now shift will now the shift will get up tensor. This up leads to this being shifted to 0, minus down tensor. This will shift to -2, plus, so this will all be divided by 2. And then this up will shift this to +2, plus down will shift to 0. So collecting the terms, we'll get the final state after step 2 will be -1/2 down tensor -2. And then I'll collect these terms. So I'll write this as 1/2 up plus down over √2 tensor 0 and plus 1/2 this term up tensor 2. I have written it such that the states inside are normalized. This is normalized, this is normalized, and the probability amplitude is over here, right? So this are the probability amplitudes, right? So again, if I measure the Walker at this stage, I will have the possibility of finding the Walker in 3 positions. So 0, 1, and 2. And then it will be, the probabilities are -1/2 square, which is 1/4. This will be also 1/2 square, 1/4. And this will be 1/2 square, which is 1/2. Again, we are doing the same thing, or we are right now in agreement with the classical Walker. Let's do one more. So I'm just going to remove this so that gets seen a little better. Okay, I'm going to do step number 3 by taking this final state of step 2 as an input to the state of step 3. Let's toss the coin first. So over here we have minus, okay, so this will be -1/2, right? So this is going to be down minus up over √2, but there is a 2 over here. So this will be 2 √2 tensor -2 plus 1/√2. The Hadamard gate takes this is like the plus state, right? So it will take the plus state to the 0 state back. So this will get back to up tensor 0. And then it will be, again, it will be plus, this guy will be 1/2 √2 up plus down over √2 tensor 2. All right. Then, so this is the coin again, this is the coin operator. And then the shift operator. So we'll do the shift operator. So let's do the shift. Okay, so this, write it over here. So this will be down. And then the down will take -2 to -3. So minus 3 over 2 square root of 2 minus up to minus 1. It will shift to the right. So this is 2 square root of 2 plus 1 over square root of 2 up tensor 1. So this is this one. And then finally plus up tensor 3 this should be, there's some mistake over here. This should be 2, right? So this is not quite right over here. This is should be 2, right? So this is going to be up over 2 square root of 2 plus down tensor 1 over 2 square root of 2. Right. So now it's important to collect the terms. So the common terms are where the position is common is these two. The remainings are easy. So let's first write the. So this is going to be down tensor minus 3 over 2 square root of 2 minus up tensor minus 1 over 2 square root of 2. And then plus, so if I collect the terms for the 1, it can write this as I can write these two terms collectively as 2 up plus down over 2 square root of 2 tensor 1. And finally, this last one, which is up tensor 3 over 2 square root of 2. All right. Now I have to write the coin space such that it is a normalized, right? So this won't do because this is not a normalized. So what we'll do is to normalize this. So in the next step, so this is just write these things before tensor minus 3 over 2 square root of 2 minus up tensor minus 1 over 2 square root of 2 plus. So if I normalize this coin space, then I get square root of, so 5 over 8 is the norm. So I'll take that out. So 5 over 8 square root out, and then 2 over square root of 5 up plus 1 over square root of 5 down. So what I've done is just normalize the coin state and taken out this 5 over 8, which is basically the norm of this vector, right? So this is tensor 1. So now both the coin and the position are normalized, and the amplitude is outside over here. Plus, and then up tensor 3 over 2 square root of 2. Okay, so this is the final state of the walker. And now if I measure the position, I will see a slightly different than the classical walk. So this is the minus 3, minus 1, 1. So the probability of finding the walker at positions minus 3 is this amplitude square. So this is 1 over 8. This is also 1 over 8. And this is also 1 over 8. Whereas this is going to be 5/8, right? This is going to be 5/8, right? Which is different from the symmetric thing that we saw in the classical walk. So in the classical walk, we had 1/8. These two were 1/8. So classical, let me just write down. Classically, they were 1/8, 1/8, 3/8, and 3/8. But this is different, right? So you see that there is a deviation between the quantum and the classical walk. Moreover, one can show that asymptotically, the walker looks completely different. In the case of the classical walk, it asymptotically, the classical walks looks like a sort of a Gaussian distribution. So this is classical, whereas the quantum walk looks completely different. In this case, it looks a little bit like this. So it looks, sorry, a little too biased towards the right hand side. So it looks sort of like this, and then it goes like this, something like this. So, but more importantly, the quantum walk. If I look at the asymptotics of the quantum walks, the variance of the ST, if I label it Q for quantum, then this is of order T square, which is quadratically faster. That means that the quantum walk is spreading out much faster than the classical walk. And so there are these very stark differences between classical and quantum walks. And the question is whether we can use it for either algorithm development or some sort of application like that. So that's the sort of brief overview of quantum walks.